So the resistance provided by the soil is a key input for the design of offshore pipeline in very soft clay. The lateral soil resistance increase significantly with embedment, and it is significantly larger for a deeply embedded pipeline as compared to a shallow embedded one. Therefore, it is very important to be able to predict the pipeline embedment in the field. So the project is the Absheron development located in the Caspian Sea, and the pipeline is a heavy pipe-in-pipe system. The soil conditions consisted of very soft clay, very close to truly normally consolidated condition, and significantly softer to what you can find at other deepwater sites. The underlying shear strength data that you see on the plot have been obtained with mini T-bar performed in box core samples that represent the best practice, current best practice to define an accurate strength profile at shallow depths. So although methodologies exist to predict pipeline embedment, there are many uncertainties. So the purpose of this back analysis is to learn from observation and apply the lessons learned to the design of the future pipeline that will be installed at the same site. So these are the observed embedment. So the initial embedment was quite large, of the order of 1.5 times the pipeline diameter. And a surprising observation is that embedment increased by another 0.5 diameter in a period of 2 years between installation and the start of the operation. So we started with the back analysis of the initial embedment. A well-accepted method is the one developed by the SafeBuck GIP. However, that method is only strictly valid for shallow embedded pipeline with an embedment of less than 0.5 diameter. Therefore, we compared it with deep embedment model that you can find in the literature. But key lesson number one is that the difference between low estimate and high estimate soil parameters has a much greater impact than the differences between the theoretical models. So it shows the importance of obtaining high quality data to narrow this range as much as possible. Another feature of the SafeBuck method is that it assumes fully remolded strengths to account for the dynamic lay effects. The problem is that it's not necessarily a valid assumption for deeply embedded pipeline. So this is the key lesson number two, because as the pipeline embeds, there's more soil restraint provided by the soil and therefore less remolding. In that particular case, only 30% to 50% remolding of the soil was observed. While it actually worked for shallow embedded pipeline, and it's been observed to be a useful proxy for a shallow embedded pipeline, but not really applicable in this case. The increase of pipeline embedment that was observed, we have two hypotheses. Additional penetration due to hydrotest can occur when it's done shortly after installation. But in that particular case, it's unlikely because hydrotest was 2 years after installation. Second hypothesis, and probably the most probable, is due to compressibility effect, due to primary and consolidation and creep. Current methods assume a bearing capacity approach, and these compressibility effects are disregarded, but we believe that in the case of heavy pipeline in a normally consolidated clay, that is something that should be taken into account. So this is a key lesson number three. Thank you for your attention and more details.
Thank you.